Okay, in this lecture series, we're going to be talking about the evolution of stars and their death. So, previously you learned about stellar birth, so how protostars evolve onto the main sequence. So our main sequence is where all the stars live out the primary part of their life. And of course you learned before that on the main sequence, stars vary in mass and therefore vary in how long they spend on the main sequence. So the main sequence is where a star has begun its fusion reaction. So before that point, it's a protostar, but once it hits the main sequence, hydrogen fusion begins. So hydrogen begins fusing into helium. So once a star enters into the main sequence stage, once that fusion reaction begins, it lands and it becomes part of the zero-age main sequence. So this is essentially where we start counting its age, right? So once it lands in the main sequence, it begins fusion and then living out its life all the way until its death. So stars evolve on the main sequence based primarily on the amount of hydrogen they initially have, their mass. So how long it will stay on the main sequence is going to vary depending on how much hydrogen they have available, in combination with how quickly they consume that hydrogen. So let's look at a main sequence star of about 0.4 solar masses and greater, okay, something like our sun. So it takes more hydrogen to produce helium in a star like our sun. So the core contracts slightly. So as the star becomes more dense, the temperature increases. This causes the outer layers to slightly expand and luminosity to increase over time. So stars like our sun, as they've evolved on the main sequence, have actually gotten a little bit larger and a little bit more luminous just on the main sequence in themselves. So there is a sense of evolution on the main sequence before the star even leaves the main sequence to go on to its death stages. So low mass stars 0.4 solar masses and below. So these are our tiny guys, okay? They're on the very lower right-hand side of the main sequence in those M-class stars. These stars are what we call red dwarf stars. They're fairly unique in the fact that they sit on the main sequence for a long, long time, and they never truly evolve past the main sequence like other stars do. These stars have the hydrogen within them spread out through the entire star, as opposed to most stars have the hydrogen concentrated in the core where that thermonuclear reaction is happening. But in red dwarf stars, the hydrogen is fused into helium throughout the entire star, okay? It's mixed throughout via convection cells. And this never gets hot enough to go to the next level of fusion. It never gets hot enough for helium to start fusing. So it's in this inevitable state of burning through all its hydrogen until it can't burn anymore and then eventually dies out. So what this means is that the red dwarf star continues to burn hydrogen for a long time. And these stars can last upwards of like hundreds of billions of years. Okay, they sit on there for a long time. Okay, so sit and think about this conceptual question before you move on. How are temperature and the fusion of elements in a star related? Okay, hopefully you answered C. To fuse heavier elements, the temperature must be high. Okay, and that's why a red dwarf star never gets to the point of fusing heavier elements. That temperature is just not high enough. Okay, so let's go back to stars with a mass close to our sun. How do they evolve after the main sequence? So once that core temperature and pressure increase, okay, they continue to burn hydrogen until all that runs out. And that core then collapses, right? Because there's no more nuclear fusion to be pushing outward. This actually causes some of the hydrogen fusion to happen faster. And what we have is kind of an interesting outward balloon effect and an inward core collapse effect. So as the core is collapsing and heating up till it finally gets to the point that it's hot enough for helium to fuse, those outer layers are actually expanding and starting to fuse some hydrogen in its expansion core, which elevates a star like our sun into the next sequence on the main on the HR diagram into the red giant phase. So take a look at this evolutionary track of sun-like mass stars to the red giant stage. So we have sorry, I'm just going to pause. I wasn't sure. Okay, I wasn't sure if my mouse was really showing that. So evolution to the red giant phase. So stars evolve, okay, on the main sequence. That's why we have the 0 age main sequence line and then the dotted line. That's how stars are evolving while they're on the main sequence itself. Once the star leaves the main sequence, that is when the hydrogen fusion stops. Okay, the star can no longer fuse hydrogen, so it wants to get hot enough in the center to start fusing helium, but that doesn't happen right away. Instead, the star evolves along, okay, these different lines. Okay, so our sun, for example, is going to actually get more luminous and expands outward into a red giant. Okay, so those outer layers actually start burning a shell of hydrogen and expanding outward while the core is expanding inward. Once that core finally gets hot enough, it can start to fuse helium into heavier elements like carbon and then oxygen. So that little asterisk, the little white asterisk, is representing a helium flash. Okay, that happens when the helium reaction begins. And this actually causes a little bit of reverse effect with the star. Those outer layers then shrink in, and the star decreases in luminosity for a bit. Now, sometimes stars can go along what's called the horizontal branch, and they can start fusion again and move up along what's called the asymptotic giant branch. So let's take a look at this. So the transition to those helium reactions. So we start off with the hydrogen fusing core, okay, a main sequence star like this. Once that hydrogen fusion stops, the core then tries to contract. So all we have left over is the helium that's not yet reacting. And instead, we have a shell of hydrogen burning gas, and this causes the star to poof out and become a red giant star. Finally, when that core contraction gets hot enough, helium fusion can begin in the center and the sun recontracts a little bit. So now we have a helium fusing core surrounded by a hydrogen fusing shell. You can see these stars end up looking kind of onion-like. Okay, so this is what I was talking about, the red giant branch, and then into the horizontal branch. So the core fusion begins in terms when the helium begins, we have the helium flash. Eventually, all of the core helium would be used up. Okay, when that happens, okay, the star shines through this fusion, and it shrinks, and the outer layers expand once again. So similar like we had before, up to this asymptotic giant branch. Now eventually the star is going to start to shed all its outer layers. Okay, so before that happens, this asymptotic giant branch, notice that we have the helium fusing shell, a carbon and oxygen core, and then that dominant hydrogen fusing shell. So with a sun-like star, masses that are similar to our sun, that center core is not going to get hot enough to do the next level of fusion. That carbon and oxygen is not going to be able to fuse because it just can't get hot enough. So instead, those outer layers start to expand outward, and they continue to expand while the center contracts. And it keeps contracting, trying to get hot enough to burn that carbon and oxygen, but it just can't do it. So what ends up happening is those outer layers expand outward, creating this planetary nebula cloud, which is not to be confused with anything involving the planets, okay? It was named that mainly because early astronomers thought it looked kind of like a planetary-like thing in the night sky, but instead, we now know it has nothing to do with planets, okay? So it's just a name that has stuck. So it's all that gas clouds expanding outward from the core contraction. That core contraction continues to happen till all that's left over is the dead star, which ends up down here on your HR diagram as a white dwarf star. And the only thing keeping that white dwarf star is what's called electron degeneracy pressure. The electrons are what's keeping the shape of the star. The star is not reacting. It is giving off a lot of temperature, okay, but low luminosity. And all of that temperature is thermal radiation from the leftover heat that was generated in the star. It's not producing any more heat itself. So this is what a white dwarf looks like, okay? Sirius, the bright star in our night sky, it has a companion star called Sirius B, and that Sirius B is a white dwarf star. So these stars are super tiny. They're only like about the size of the Earth, okay? 5,000 to 6,000 kilometers in size. And they're mainly held up, like I said, by degenerate pressure, okay, in terms of the electrons. Okay, You can read this slide. I'm going to skip over. I'm starting to run out of time for this first lecture. So the gas that's left off from the white dwarf star, that's the planetary nebula. That's all those hydrogen and helium fusing layers that are expanding out into the sky. Now these pictures look flat, two-dimensional. You have to remember the star was spherical. So these are actually spherical round, so it's coming at you and behind you, so it's a round shape. And this gas will eventually just dissipate out into space and populate the universe with all of those elements that the star created. Okay, so here's another image, the planetary nebula. So this is how our sun is going to die, as a planetary nebula with the white dwarf star left over. So here's a brief overview of how low to average mass stars live out their life and then eventually die. Okay, next we will cover high mass stars in the next video.